This is the second video in the midterm review, and this will cover Unit 2, which is entitled Characteristics of Matter and the Atom. To start with, let's discuss the basic states of matter. You have a solid, which will have a defined shape and volume, and the particles will be very close together, as shown with the picture on the far right. You have a liquid, which will have a constant volume, but will take the shape of the container, which is, and the particles are going to be a little further apart and almost flow over each other, shown by the picture in the middle on the bottom. And you have a gas, which is going to have an undefined shape and undefined volume. The particles are very far apart, as shown by the picture on the far left, and this and the gas is going to take the container going to take the volume of whatever container it is in. Any substance that you have is going to have some sort of property, and there are two basic types of properties. The first is a physical property, and this is basically any property that can be observed or measured without changing the composition of the actual substance. There are two types of physical properties. First is extensive, which is dependent on how much of the substance you have, something such as the length or the volume. And intensive is independent of the amount of substance you have, and an example would be like the density or the boiling point or the melting point. And a kind of way to remember this is intensive is independent of the amount of stuff you have, whereas extensive is dependent. And then the other type of property you can have is a chemical property. And basically this describes any property that allows the substance to combine or change into something else. Essentially, there's not really a whole bunch of chemical properties. It's really just talking more about the reactivity, which is an example of a chemical property. Another thing with a substance is that they can undergo changes. And we have two types of changes. A physical change is something that will alter the substance without changing its composition, similar to a physical property. And a chemical change is something that will actually change the substance itself. And there's four things you can look for when you are looking for a physical or chemical change. Excuse me. A change in color, a change in odor, which means like a smell, a change in temperature, or the formation of a gas or a solid. Often the change in odor is going to be related to the formation of a gas, and the change in color is going to be linked to the creation of a solid. All substances can be classified in different ways. You can either have a substance, like a pure substance, or you can have a mixture. Pure substance can be broken down into either an element or a compound. Elements are our most basic material. It cannot be broken down any further than an element. A compound is one or two or more different elements that are chemically combined. In this sense, we're using molecule and compound in the same sense, so it can actually be two elements that are chemically bonded together. A mixture is two or more pure substances that retain their chemical properties, meaning that you can separate them apart. We have two types of mixtures. We have heterogeneous, where everything looks the same. Heterogeneous, where you can pick out the different parts of the mixture. An example of this would be something like, let me get my pen here. Something of that nature would be like trail mix. Would be an example of a heterogeneous. Homogeneous is, as I was saying before, is something that has a consistent composition. We also call these solutions. So something like this would be sweet tea, or like Kool-Aid. You won't see the individual parts of the powder or the tea mixed with water. It's going to look as if everything is completely the same. Alright. Matter itself can be dictated by three rules, or three laws. The first is the law of conservation of mass. And what this says is that mass is neither created nor destroyed. And this is particular to a chemical reaction. So when you look at a chemical reaction, the mass of the reactants, is basically what you start with, should equal the mass of the products, or what you end with. The second law that we're going to discuss is the law of definite proportions. And what this says is that regardless of what mass of elements you have for a compound, they are always going to be in the same ratio. So in this case, we introduce something known as percent by mass. And what this is, it's a calculation where you're going to take the mass of an individual element, divide it by the mass of the total compound, and multiply by 100. Another way of thinking about this is it's the part of the compound over the whole mass of the compound. So the part over the whole. So the percent by mass of, let's say, hydrogen and water will always be the same no matter if you have 1 gram of water or 1,000 grams of water. Finally, the law of multiple proportions deals with different compounds that share the same elements. What this says is that regardless of what the masses of each element are, they will always combine in a small whole number ratio to one another in almost like a series. So an example would be like nitrogen monoxide, nitrogen dioxide, nitrogen trioxide. It's nitrogen trioxide is 1:3, nitrogen monoxide is 1:1, nitrogen dioxide is 1:2. These are they're whole number ratios between nitrogen and oxygen, and they're always going to be those whole number ratios. Alright, let's look at an example where we apply the law of conservation of mass. It says a reaction of 22.85 grams of sodium hydroxide with 20.82 grams of hydrogen chloride gives off 10.29 grams of water and sodium chloride. What is the mass of sodium chloride? Well, to figure this out, we have to take the mass of the sodium hydroxide and the mass of the hydrogen chloride, which is our reactants, is what we're starting with, and we're going to set that equal to the mass of the water plus the mass of the sodium chloride. And the mass of the sodium chloride is what we don't know. So in this case, that's what we're going to try to find. So we take 22.85 plus 20.82 equals 10.29 plus X. And again, X is going to be the mass of our sodium hydroxide. So when we calculate that out, we get a mass of 33.38 grams for the sodium chloride. I misspoke earlier. It's not sodium hydroxide, it's sodium chloride that we're looking for. And this is a application of the law of conservation of mass. And this employs the equation: the mass of the reactants equals the mass of the products, which will be given on your midterm. Alright, now let's talk about the law of definite proportions. And this is the percent by mass equation. And again, the percent by mass equation is what's going to be used, which will be given to you on the midterm. Okay? So, in this question, we have a 2.89 gram of sulfur reacts with 5.72 grams of copper to form a black compound. They want to know what is the percent by mass of sulfur. So we take the mass of sulfur, which is 2.89 grams, we take the total mass, which we get by adding the 2.89 grams to the 5.72 grams, and we multiply by 100. When we do that, we end up with 33.6 grams, or 6% sulfur. Alright, so earlier we were talking about mixtures and how they can be separated out. Well, there's 4 techniques that we've discussed that are ways to separate out different types of mixtures. The first is filtration, and this is where you use some sort of porous barrier to separate a solid from a liquid. And so this is based on size of particle. The next is distillation, and this is where you are differentiating based on the boiling point. You heat to just below the boiling point of one liquid. This is a mixture. This is going to be a mixture of liquids. You heat to just below the mixture of one liquid. Excuse me, the boiling point of one liquid, and you then run that liquid, or you heat that to a gas. You run that through a condenser, which is that kind of funny thing that had 2 parts, like an up and a down part, if you recall from class. And then we collect that liquid in another flask. Our third technique is crystallization, and this is where you basically use evaporation to remove any excess liquid from a solid that's formed, or not from a solid that's formed, but from a solid that's in solution. And if you get rid of all the water, then you get all of the solid that is left over. You could also think of this in terms of adding something to create a solid to force something out of solution, basically creating a precipitant, which we'll talk about later. And finally, chromatography, which separates something based on how well it travels across a surface. So with this, the way I described it is we're separating ink. So you have a piece of paper, often like a paper towel or a filter paper. You put your ink dots down at the bottom. You run water up the paper, and you get different spots along the way, and it separates based on size. So in this case, we have 2 things. You have the mobile phase, which is your mixture, so it's the water that's picked up with the example, the mixture, which is the water / ink, and the separation, the stationary material, which is our separation material, which is going to be your filter paper. Okay, and again, this is separated based on the size of the particle, and also kind of how well the mixture will dissolve in the liquid or whatever. Alright, so let's move away from material, from the matter now, and let's talk about the basic thing to chemistry, which is the atom. And the atom has been around for a very long time, but there's been certain key developments along the way. And yes, you are responsible for knowing these people, so I strongly suggest you write these down somewhere. The first big person was Democritus, and he said that matter is composed of atoms. You should read atoms. And that they are of different sizes and shape. A short while after that, Aristotle said, no, that's incorrect. Matter is actually made of earth, fire, air, and water. And this was the standing view until about the mid-1800s, when John Dalton went back to what Democritus said and said, no, atoms are actually made, or matter is made of atoms, and that these atoms cannot be created or destroyed in a chemical reaction. So basically, John Dalton's who's responsible for the law of conservation of mass and matter. Same idea. Then J.J. Thomson figured out the charge to mass ratio of an electron, and he proposed what we call the plum pudding model. That's where you have basically a substance of positive ions, and in between these positive ions are floating electrons. Almost think about it as like a chocolate chip cookie. The batter itself is the positive material, the chocolate chips are the negative ions. Robert Milken actually determined what the mass of the electron was, and then Ernest Rutherford proposed the existence of the nucleus and of protons. So basically, he disproved the plum pudding model, and in his instance, he said that the center of the atom is going to have a massive positive charge, and the electrons are going to be floating around on the outside. And finally, James Chadwick proposed the existence of the neutrons within the nucleus also. Alright, so we have two basic parts of an atom. You've got the nucleus in the middle, and you've got an electron cloud on the outside. The nucleus itself is going to have positive particles, which we call protons, and neutral particles, which I'm going to signify with a 0, which we call neutrons. The electron cloud is going to have negatively charged particles, which we call electrons. That's the name, electron cloud. Alright, based on what element it is, there are certain ways and certain things about the element that will tell us how many protons, electrons, and neutrons there are. The first thing is the atomic number. This signifies how many protons are in the atom. This is how you identify the element. So the atomic number identifies the element. It's symbolized by Z often, and if you have a neutral atom, which means you have no charge, the number of electrons will equal the number of protons. Now, if you do have a charge on the atom, you will just figure this out by taking the number of protons minus the number of neutrons. And anything that has a charge we call an ion. The last bit is known as the mass number, and this is the sum of the protons and the neutrons within the nucleus. You will see it written in two ways. You will see it written as the name of the element with the mass number at the end, in this case sodium 23, or if you look down here in the lower left corner, there's another way we can write the atomic notation. You have the symbol, which in this case is sodium. If there is a charge, it's going to be in the upper right corner. The mass number, in this case is 23, is in the upper left corner, and the atomic number for sodium, which is 11, is in the lower left corner. So it's important to understand how to write the atomic notation for different elements. So here's an example. An atom's nucleus has 92 protons, and its mass number is 235. How many neutrons does this atom have, and what is the element? Or what is the atom, excuse me. So, to figure out the neutrons, all you're going to do is subtract you're going to say 235 minus 92, which will give us 143. So remember, the mass number is the total of the protons and the neutrons, so you just subtract the protons from the mass number to get the number of neutrons. To identify what element it is, well, we can just look at the number of protons. 92 protons means that it's number 92, which is uranium. Now, if we wanted to write the notation, the atomic notation for this, we would do U, which is the symbol of uranium. We'd write 235 in the upper left corner, 92 in the lower left corner, and in this case we have a neutral atom, so it would have no charge. Now, we have an idea known as an isotope, and these are atoms that have the same number of protons but a different number of neutrons. And the way that we calculate the atomic mass, which is the number that's given on the periodic table, is that it's a weighted average between all of the naturally occurring isotopes and their masses. So if you look on the periodic table, most elements are going to be written in a grid. You're going to have, let's say we'll use sodium. You're going to have the element symbol in the middle. At the top you will have the atomic number. Sometimes you'll have the name. And at the bottom you will have the mass. and this is your atomic mass at the bottom. Again, this is a weighted average of all of the naturally occurring isotopes. And it's measured in atomic mass units, which you'll often see symbolized AMU. And the way we calculate the atomic mass, the average atomic mass, we take the mass of one isotope times its abundance, and this has to be in decimal form because it's a percent, plus the mass of the second isotope times its abundance, and so on. Often you'll have 2, 3, maybe 4 sometimes isotopes, but it's not more than that often. So an example, gallium occurs as Ga69, which is a mass of 68.926 AMUs with 60% or 60.108% abundance, and Ga71, which is a mass of 70.925 AMUs with 39.892% abundance. And they want us to calculate the atomic mass. So you take the mass of the first isotope times its abundance, and again it has to be in decimal form, so we remove the decimal 2 places to go from percent to a decimal. We take the second mass and we multiply it by its percentage. Again, we move it the decimal 2 places to the left to get it in decimal form, and then we add those together, and when we do, we get 69.723 AMUs. So the atomic mass of gallium on your periodic table should read something close to 69.723. The final thing that was covered in Unit 2 was nuclear reactions. And nuclear reactions are anything that involve the atom's nucleus. There are 2 basic types of nuclear reactions. There's nuclear fission, which is where you split a nucleus into fragments, and this is what you often see in power plants or atomic weapons. And then the other type of reaction is nuclear fusion, which is where you combine atomic nuclei, and this is what occurs in the sun. Also within the nucleus you can have radioactive decay, and this is where you have unstable nuclei that lose energy by emitting different types of radiation. And there's 3 types of radiation. The first is alpha radiation, and this is where you give off an alpha particle. An alpha particle is either symbolized by the alpha symbol, which is shown here, or the one I just drew, or by basically it's a helium nuclei. It has 2 protons, 2 neutrons with a +2 charge. The second type of radiation is beta radiation, and a beta particle is basically an electron. It's either symbolized by the beta symbol, or it is, actually I made a mistake there, let me correct that real quick. It is symbolized basically by an electron. It does have a -1 charge. So if we were to write it in atomic notation, it has no mass, it has a -1 atomic number, okay, and it has an E as a symbol. And the third type is gamma radiation, or gamma ray, and this is just simply signified by a gamma, and it has no mass or electrical charge. It's just excess energy. So we can actually take these and write balanced nuclear equations to show how the nuclei that emit these radiation, or these that undergo this type of decay, will actually, what they'll create. So in the example, we have boron-10 emits alpha particles, and cesium-137 emits beta particles, and they want us to write the balanced nuclear equation for both. Alright, so first you've got to write each element as its atomic notation. So we have a mass number of 10 for boron. If you look up the atomic number, it's 5. Well, it's going to undergo alpha radiation, so you're going to give off an alpha particle, which is, like I said, a helium nuclei. And the thing about this is it has to keep the conservation of mass. So the numbers on top and bottom both have to equal each other. So if we know that we're going to give off 4 mass numbers, that means we have 6 as a mass number, and then the same if we're going to lose 2 protons, that means we're going to have 3 protons left over. So once we get those numbers, we can look on our periodic table, figure out what atomic number 3 is, which in this case is lithium, and that completes our balanced equation. If we do the beta radiation, it's the same thing. We write cesium in its atomic notation, we're giving off an electron basically, okay? So we have no change in the mass, but we're actually gaining, in a way, we're gaining a proton. So because these have to equal 55, and when we look up what 56 is, it becomes barium. So basically you're creating a barium atom.